All right, so this bringing together of algebra and geometry that's inherent in the Cartesian revolution also brought some philosophical difficulties. Not just philosophical difficulties, some mathematical difficulties. And some of these difficulties are still around with us today. So when we are solving polynomial equations, we saw that mathematicians of antiquity and the Arab and the Hindu mathematicians did not regard all numbers as equal. Okay? All numbers are not equal. This was sort of the ancient view. The numbers that are the simplest are the natural numbers. The next ones that are the next simplest would be the fractions, 2 over 3 or 22 over 7. Negative numbers and 0 are more problematic. We saw that it took a long while for people to actually introduce a number called 0 as part of the arithmetic. It was one of the great advances of the Hindus. And negative numbers, well, they were highly problematic for a long time. What does negative 1 mean? What does negative 2 mean? What does negative 3? What are these numbers? You can write them down, but what do they mean? It's clear what we mean by 2 apples. It's clear what we mean by 5 apples. Even 2/3 of an apple, okay, we can understand what that means. What does minus 2 apples mean? Well, these days we say something like, well, it means that I owe you 2 apples. Or something like that. Well, but that's a lot less convincing than actually having 2 apples. I can show you 2 apples. How do I show you here is minus 2 apples? Look at the difference between minus 2 apples and minus 5 apples. Right? You know? Negative numbers were highly problematic. The Arabs, the Hindus, the Greeks, even Descartes was nervous about negative numbers. Even in the 1600s that we're talking about now, negative numbers were not accepted so readily. For example, a famous conundrum was that suppose that negative numbers exist, then minus 1 to 1 has to equal 1 to minus 1, right? In terms of a ratio. This proportion is the same as this proportion. And people said, well, that's absurd because this one's smaller than this. So how can the smaller to the greater be the same as the greater to the smaller? Right? We're used to things like 2 to 4 being the same as 3 to 6. Okay, the smaller to the greater is the same as the smaller to the greater. How can that work? But eventually people realize, well, we need negative numbers because we want to solve equations. We want to solve equations like 3x plus 1 equals, 3x plus 4 equals 2. And when you just go through the motions, eventually you're going to get minus 2/3. You want that negative number to be there, to be able to do arithmetic consistently. So people basically just forced negative numbers, said, look, we're going to use negative numbers. And in fact, it's kind of interesting that almost the geometry came to the rescue of the algebra. Because this connection between numbers and geometry allowed people to think about numbers in a new way. It went both ways. So once you think about the numbers as being on a number line, then it's not so hard to see what the negative numbers mean. The negative numbers are just the positions to the left of 0, just as the positive numbers are the ones to the right of 0. So geometrically, the role of negative numbers is not so hard once you think in terms of a number line. These days, young people are indoctrinated into thinking this way. You've all been taught the number line from an early age. Okay? You've been taught that numbers are really positions on the line. But that's not the way ancients thought about it. Numbers were things that you counted with. And counting is a lot different from actually a position on the number line. In particular, the Greeks, the ancient Greeks would have objected strenuously to this mixing or merging of numbers with geometry. They purposefully kept these two things apart in their minds. To them, lengths and numbers were quite different things. To the ancient Greeks, lengths and numbers, well, lengths really were segments. These were different. And it was not proper to mix them together. One really wanted a barrier there. A good example of that is the attitude towards irrational numbers. Okay, irrational numbers were highly problematic also for a long time. We've already seen this irrational number. That caused a lot of problems even for the Pythagoreans 600 years before Christ. Remember? That big to-do that they made by realizing that the diagonal of the square was not commensurable with the side. To the ancient Greeks, they would have said, look, it's no problem. If that's a segment 1, we can cook up another segment which you can call root 2. So this is constructible. Geometrically. But arithmetically, finding out what root 2 is so much harder. If you want to calculate root 2, 1.414, whatever it is, okay, we've seen that there's an algorithm to do that, but the algorithm needs to keep going in order to generate more and more decimals. At no point did you actually get to the end of that algorithm and you can stop and say, finished, now I've calculated root 2. You never end up calculating root 2. Arithmetically, root 2 is an ideal. It's some kind of dream. Okay, it's beyond the horizon. We can say, well, it's over there somewhere. We can't see it, but it's over there. What we actually in practice do is just truncate it and say, all right, that's root 2. That's what the engineers work with. But the real root 2 just keeps on going past the end of time. It's lost to us. So the ancient Greeks would have said, so you see, numbers and lengths are not the same thing. We can construct geometrically a root 2 very simply. Our compass does that. But arithmetically, it's a completely different story. So the ancient Greeks would not have been happy with this bringing together of numbers and geometry. They would have said, no, we object. That's wrong. What are you people doing? You're confused. Well, habit is a good master, right? Everybody else around us believes it, and if it's all in our books, we end up saying, yeah, I guess it works. And that's sort of what we do. That's why it's interesting to go back in time and see how other people thought about things who don't have the same unanimity of opinion as we do today. So I'm going to read you something from another very lovely book. This is a book by Morris Klein. It's a very encyclopedic treatment of the history of mathematics. And if you've finished Stilwell and you'd like to go on to something which is even more in-depth, Morris Klein's book, Mathematical Thought from Ancient to Modern Times, in 3 volumes is excellent. Okay? It's a 3-volume thing. Here's volume 1. And I'm going to quote to you from a mathematician whose name is Stifel, who wrote a book called Arithmetica Integra in 1544. And he writes in a remarkably modern voice. He's talking about irrational numbers. He's talking about the difficulties of working with irrationals in decimal form. Here's what he says. Since in proving geometrical figures, when rational numbers fail us, irrational numbers take their place and prove exactly those things which rational numbers could not prove. We are moved and compelled to assert that they truly are numbers. Compelled, that is, by the results which follow from their use. Results which we perceive to be real, certain, and constant. On the other hand, other considerations compel us to deny that irrational numbers are numbers at all. To wit, when we seek to subject them to numeration, in other words, decimal representation, we find that they flee away perpetually, so that not one of them can be apprehended precisely in itself. Now, that cannot be called a true number, which is of such a nature that it lacks precision. Therefore, just as an infinite number is not a number, so an irrational number is not a true number, but lies hidden in a kind of cloud of infinity. So he's voicing a view which was very common until relatively recently. Nevertheless, there are some kind of irrational numbers which are nicer than others. And Euclid knew which ones they were. So although all irrational numbers may have some problems, some irrationals are nicer than others. And Euclid knew which ones they were. He knew that the rational numbers obtained by square roots and by repeated square roots were reasonably decent numbers, like root 2 or root 5 or square root of 1 plus root 5 and so on. So these are very small class of all irrational numbers, but they are still kind of amenable in some ways. First of all, they correspond to geometrical constructions. So when I say that Euclid worked with these numbers, it's not really true that he worked with these numbers. What he did is he worked with segments which to us represent the numbers. He worked with the geometry, the geometrical analogs of the numbers, not with the numbers themselves. And since his constructions just involved the ruler and the compass, he was quite happy with those constructions. These particular irrationals also have another way in which they're particularly simple, and that's when we look at them with the viewpoint of continued fractions. So here's an infinite continued fraction, where we have 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus blah, blah, blah. Okay, you might ask, well, what does this mean? And one way of making sense of it is to say, well, all right, let's let it be x. Whatever it is, let's call it x. Then it's certainly equal to 1 plus 1 over. Then if you look at what this thing is, it looks a lot like x. Again. In fact, it's exactly x. It's 1 plus 1 over 1 plus 1 over. So that's exactly x there. So we have this relation that x happens to equal 1 plus 1 over x. Now, if we forget about the continued fraction and just concentrate on this, it's a quadratic equation. And it's the quadratic equation x squared minus x minus 1 equals 0. A very famous quadratic equation. Its solutions are plus minus b plus or minus square root of b squared minus 4ac all over 2. So in Descartes' day, we would have thrown away the negative solution and just said there's only one solution, 1 plus root 5 on 2, which is the sort of a golden ratio kind of number. 1.6180339887, and it keeps going in some weird, mysterious way. And it was Lagrange sometime later, famous French mathematician Lagrange, whose dates are 1736 to 1813, who proved that continued fractions like this, which are periodic, so periodic continued fractions So that means ones that are infinite, but the infinite pattern repeats. In this case, it's the most simplest kind of repetition, but you can imagine one where this is 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. That kind of periodic continued fraction corresponds exactly to a quadratic irrational, namely a zero of a quadratic equation with integer coefficients. So this is another way of getting at irrational numbers. Instead of thinking about them as being infinite decimals, we can think of them as being infinite continued fractions. That's a little bit more canonical than decimals because it doesn't require a base 10 system. So for example, you could take pi, and you can think of pi as being the ratio pi over 1. And if you think about applying the Euclidean division algorithm to it, you write it as 3 plus some remainder. Okay, and the remainder, well, the remainder would be pi minus 3. Okay, but that remainder is less than 1. So we can write it now as, we take that remainder and replace it with 1 over itself. That's what we did before, so it's 1 over pi minus 3. And now we can think about this number and find, well, do the division algorithm on it. That's going to be an integer plus some remainder. So it turns out that that's 1 over 7 plus some other stuff. And then if you keep on going, it's 3 plus 1 over 7 plus 1 over 15 plus some other stuff. And ultimately you can proceed as far as you want. And here's what it looks like. Okay, it becomes cumbersome to keep writing down. So instead of doing that, we'll just summarize. It starts with a 3, and then 7, 15, 1, 292, 1, 1, 1, 2, 1, 3, 1, 14, 2, 1, 1, dot, dot, dot. It's also an infinite sequence. It's also hard to predict what the elements are, but it's, first of all, more canonical than the decimal representation of pi, and moreover, it gives you the best fractional approximations to pi. So if you ever forget what pi is and you want to figure it out, just remember 3, 7, 15, 1. Okay? So if you just remember 3, then the first approximation is 3. If you remember 3 and 7, then you know that it should be 3 plus 1 over 7, which is 22 over 7. If you happen to remember the 15 as well, then you know it's 3 plus 1 over 7 plus 1 over 15, which is 333 over 106. And if you remember the next one, 3 plus 1 over 7 plus 1 over 15 plus 1 over 1, then you get the approximation 355 over 113. And automatically the continued fraction gives you the best, in some sense, the best rational approximations to any irrational number. But still, there's the problem of, what exactly, how do we control this infinite sequence? Whether we're working with this continued fraction or whether we're working with 3.1415926, blah, 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 how do we actually say what pi is? How do we get around this ambiguity of the infinite decimal nature that Stifel was pointing out? Well, these days we have an answer to this. We say, all right, it's true, we don't know this entire decimal expansion. What we'll do instead is we'll work with the computer program that generates this. You can write a computer program, half a page long, that generates this sequence. Okay, so there's a little program. It's half a page long. It's written in Fortran or whatever language you like. And we'll say, all right, instead of thinking about the decimal number, we'll just think about the program that generates it. That's finite. We can think of the number as actually being the program. That's a very nice idea. But with this subject, you know, you fix one part of the problem and it pops up somewhere else. Okay? The problem now is that somebody else can come along with another program for pi, which is quite different from your program, because it uses a completely different idea for pi. And now the question is, how do I know that these two programs are the same? Because there's lots of formulas for pi. You can take any formula for pi and use it to generate a program. Or what I could do is I could simply take your program and I could do the following thing to it. I'm going to modify your program by adding one little line that says, all right, when you're calculating the nth decimal, what we're going to do is we're going to calculate, we'll take that n, so this is the first decimal, second, third, fourth, fifth. If you take n, for every n, I'm going to calculate if n is an odd number. Yeah, a little thing. If n is an odd number, and if n is a perfect number. Remember what perfect means? Perfect means that the sum of its divisors less than itself equals itself. So if 5 happens to be an odd number and a perfect number, then what I'm going to do is I'm going to modify the decimal by adding 1 to it, mod 10. That's a new program. Is that program the same as the program that you wrote down? 1159. No one knows whether that program is the same program, because nobody knows if there is an odd perfect number. We know about even perfect numbers because Euclid told us about them. But no one knows whether there's an odd perfect number. So even I can build that into the computer program, but it means that you don't know whether your program and my modification are actually the same or not. We know that there's no odd perfect number till at least a few trillion. So certainly your value for pi and my pi agree to the first few trillion places. But whether they completely agree or not is an open question. So problems with real numbers and irrationals, they're still around, but people work hard to say, problems? I don't see any problems, do you? But when we study mathematics history, we do learn about those things. Okay, so in our next lecture, we're going to talk about projective geometry, which was necessary for the 17th century mathematicians to start grappling with the real nature of curves and equations. So we'll see you then.